Okay, welcome to the video on partial fraction decomposition technique for solving integrals which contain polynomials that could be factored out. Okay, since in the last video we talked about, how to tackle quadratics. When you see quadratics in different forms, sometimes it's easier to convert it into one form or to the other and solve them, right? And then we concluded that whenever we can factor, right, we should use partial fractions. So now, before we begin the method, I want to give you a bunch of disclaimers about this, okay? This method is not an integration method, okay? Partial fraction decomposition is a method of algebra, okay? What it does is it helps you to break down a single expression, okay, which has two factors being multiplied in the bottom. So if you zoom in here, right, you see that expression here. When you have the polynomial written as two factors, one of them being x plus a, the other one being x plus b, you can break them down into summation of two separate fractions, each containing one factor each. Okay, that's why it's called decomposition. Okay, what it does is it'll take this guy and this guy, right? So there are two factors, and break down into two different fractions into, these two pieces which contain one factor each. And when you have terms with one factor each, they're easy to integrate. So that's what we're trying to aim into this method, okay? This method will only help us expand this out. So first of all, we need to verify when can we use this method, okay? I'm going to get rid of this all arrows and stuff. And now let's look at the rules. So when can you use it? It said that you can use it as in when you get an integrand in a form like this, when you have it in terms of a rational expression, where you have p over q, right? Some kind of thing. Where degree of polynomial px, which is the numerator, is less than the degree of the denominator, which means you have a denominator that's bigger than the numerator. So like, something with a linear and a quadratic at the bottom, something with a quadratic and a cubic at the bottom, right? So the degree of the denominator needs to be higher for this method to work, okay? If that's not true, okay, if you see the degree of px is bigger than the qx, then you have to do log division first, okay? We'll talk about that once we have an example like that coming up, okay? But for now, we got to make sure we know this. Now, the rules that govern this, okay, there's going to be two of them, okay? The rules, I'm going to write them here. Rules. Number one, okay? When you know the number of factors you have will determine how many terms you'll have, right? By just eyeballing it, right? So if you look at this case, you have two factors, you're going to break them up into two terms, right? One being a over x plus a, and then b over x plus b, right? When you have, let's say, two factors here, you again have two things being decomposed like that, right? So those two can be broken down to like two separate terms again. However, in this case, you have to see that you have two factors, but one of them is repeating thrice because it's raised to the power of 3, right? So in essence, what you have is two factors, good, but one of them is repeating 3 times. So in total, you have 3 factors, one repeating one kind, and then one more. So total 4 factors, right? So that's why when you see this side, it has 4 expanded terms into it, okay? So that's rule 1. So if you think about it that way, let me just get the eraser out of the way. So rule number 1 tells you that the number of factors, okay, this includes the repeating ones. So you got to see the number of factors. The number of factors will determine the expansion, okay? When you expand it or decompose it, any word you want to use it, the number of terms you'll have in your expansion depends upon how many factors you have. Cool, that's easy, out of the way. The second rule, however, is saying that the degree of the numerator will be 1 less than the denominator. So let's look back here. When you see this expression here, in this case, this is a linear factor, right? The terms inside have a linear factor. So x is raised to the power of 1. The numerator has to have a degree less than that. So what's the less than 1? It's 0. So a 0 degree polynomial is just a constant on top. So whenever you have a linear factor, you're going to have a constant in the numerator. Same thing goes here. You have a linear factor, and constant on the top. However, in the second example, you see this factor is a quadratic factor, right? It has an x squared on top. So when you're trying to write its numerator, that its numerator needs to be 1 less than the quadratic, which is a linear. So that's why this whole thing on top is a linear. And how do you write a linear? A linear has to be composed of two things. One x term, and then you have a constant term, right? So that's how you decipher what is going to be on the numerator. However, for the x plus a here, that's still a linear factor. So all you're going to get is a constant on top. Okay, so that's how the rule works. If you have a quadratic, the top is going to be a linear. If you have a linear, the top is going to be a constant. And that's probably as hard as it can ever get. You're never going to get cubic factors in there. Okay, if you get a cubic factor, then the top has to be a quadratic, which is just, you know, defeating the purpose of solving the problem to begin with. So that's what we're trying to aim towards. Okay, that's this. Easy. Now the last rule here is a rule of multiplicity. So I'm going to write that in here. So third rule is the multiplicity. Multiplicity is nothing but just telling you how many times a factor repeats. So you got to watch that thing. So the last thing that we saw here is that, you know, you had a factor repeating here. So you have x plus a. What kind of factor it is? It's a linear factor. So the numerators of all these linear factors is going to be a constant. That's rule number 2. That's already taken care of that. So that's this. But repeating it 3 times will give you a nice sequence that looks like this. So the constants are going to be the numerators every single time. For the first time, what you do is you start off and write this once, right? Just once. Then you write another term with x plus a squared. And then you got to write another one of x plus a cubed. And you got to stop at the cube, because once you match up this power, you got to stop there. So let's say if you had an expression that looks like, you know, a 4 there, you will write 4 terms, one with 1, another one with 2, then with a 3, and then with a 4. Okay, and then what kind of numerators all of these terms will have is determined by rule 2. It directly depends upon what factor you have inside. This is not a quadratic factor. This is a factor which is a linear, but it's repeating twice, okay, or has a multiplicity of 2. That's what you got to remember. So in this case, you have basically 4 factors, so 4 terms, right? And the first one will be written as with x plus a to the 1. Second one will be written as x plus a squared, then x plus a 3, because you have a 3 there, you stop there, and the last one was x plus b. And x plus b is also a linear factor, so the top has to be a constant. So these are just the rules, okay? Everything that you have to do is you have to like find this relationship first. Once you have this setup done, then you have to solve for a and b. Okay, so first of all, you do the setup and then you solve for a and b, and from that point onwards, you can compute an integral. Now what we're going to do is we're going to write a few expansions to get you familiar with the rules. Okay, so I'm going to take some examples. I'm going to try to write those expansions here so you guys can agree on things, right? So let's say I have this integral. I'm going to save you the hassle. I'm going to give you the factor forms just because I want to make sure that you get the rules. So x plus 2, and x minus 3. So right now what we have is a polynomial that is broken down into 3 factors at the bottom. The first factor being the x, right? Second factor being x plus 2, and then x minus 3. So now what you see here are all the factors that are linear. So how many are there will determine how many terms you'll have, first of all, right? So you're going to have 3 of them. So 3 of them, and then you're going to add them up, right? That's the default. So you're going to add up 3 terms. The first term will have the factor x as the denominator because that's the first factor. Then you have x plus 2. Then you have x minus 3. Now because all of these factors are, you know, linears, the tops are going to be 1 less, which are constants. So that's the expansion of that. Okay, let's do one more example here to clarify. Let's say you have this. So the reason why I take this tricky example is because it kind of gives you, you know, the feeling of ambiguity. Because here, some people would agree that x squared is a quadratic factor, right? The first one here, the x squared, is a quadratic factor. Some people will agree that it could be a linear factor repeating twice. So how do you know the difference? Because in this case, if I were to write a square there, it's clear that this is a linear factor with a square, which means it's repeating twice. But when you don't have any parentheses around it, it kind of causes confusion. And you get confused whether it's going to be an x squared, just as a quadratic thing, or do you want to take it as, you know, x repeating twice? Okay, so the thing that you can do here is both ways are correct. So there's no one single correct way of interpreting it. Whatever you see, as long as you're consistent with the rules, the expansion will be no different. Okay, so in this case, what I will do is I'll treat this as a quadratic factor. Okay, so now I have a quadratic factor here and I have a linear factor here. So in this case, I have two factors. So my expansion is going to have two terms, right? That's easy. One of them is going to have the factor x squared. One of them is going to have the factor x minus 2 as a denominator. So now because this is a quadratic factor, the top has to be a linear. So the linear is going to be ax plus b. A linear has two unknowns. Okay, so a and b will become its two unknowns. However, this guy is a linear, so the top has to be a constant. And that's the expansion for this guy. I'm not solving a, b, and c for now because I'm just trying to give you, you know, the point of view of how you want to actually, you know, look at that. It's cool, so we're good with this. Let's do one crazy one. Okay, let's see if you guys can contemplate on that. So okay, even though this is not supposed to be tested, but I want to, you know, just emphasize the rules. We're just going to focus on writing the expansion of this. Okay, so the first rule is, how many factors do you think we have? We have this factor repeating twice, we have this factor repeating thrice, and we have this factor repeating only once. So in total, we have 6 factors. Okay, so we're going to have 6 terms. So this, 2, 3, 4, 5, 6. 6 terms. Nice. So now each one of them is going to have those factors in the way. And now because of repeating factors, you know, because x plus 1 squared, the rule is to start off by x plus 1 to the power of 1, and then keep on increasing the power of 1 until you hit the max. So in this case, the bottom will be x plus 1 raised to the power of 1. That's a gigantic eraser, my bad. Just x plus 1. The second time you'll write the same thing, but now raised to the power of 2, right? And that's the maximum we ever go, so we can stop there. That's the expansion for x plus 1. Okay, and then we have what? We have x plus 2 to the cube. So that's repeating thrice. We're going to start with 1. So we have x plus 2, 1. And we're going to raise that to a squared, and then raise to be a 3, and stop. So you're going to be like writing them in pieces, incrementing the power by 1. Once you hit the max, you stop there. So that's the expansion for the first 5 repeating factors. The last one is x squared plus 4. So that's just a regular quadratic factor, right? Now, to write the numerators, you have to see what the factor is, right? All of these are linears, right? So all of these are going to be constants. This is also linear, so D, and then I'm going to call E. But now the last one is a quadratic, right? So you have an x squared plus 4 as a quadratic factor. The top has to be 1 less than that, so that's a linear. So the top here will be E. So fx plus g. It'll have 2 unknowns, okay? So that's how these expansions will kind of work around. Just to get the rules across. Once that's done, let's begin the problems. Try to see if we can solve some questions, using the technique or not. So the first example that I'm going to cover is going to be very straightforward. And that's going to be, just something that I'll give it to you. So let's say question 1. We have it as integral of 2x this. So we got 2 factors at the bottom. And we know we got to use by partial fractions here. So now the reason is, right now, what we want to do is we want to say that 2x over x plus 3 and 3x plus 1 could be decomposed, okay? Could be decomposed into two separate fractions, okay? One of the factor needs to be x plus 3, and then the other factor is going to be 3x plus 1, right? And then because both of these factors are linears, the tops have to be one less, which is constants. So we got these. Cool. If we can say that this is true, right, we have to solve for a and b such that it's true, right? This was just like an exercise in expansion. So once you want to actually solve for that, let's do it, okay? In this case, if you're saying that this is true, then let's try to simplify this expression by cross multiplying it, right? So I'm gonna write the left side as it is. It's just gonna be the same. However, if you cross multiply, or like trying to make the common denominator here, this guy here, the x plus 3 term, I'm gonna try to go piece by piece, because like this is where sometimes people get tricky. So a over, so this already has the x plus 3 factor. It only needs a 3x plus 1 factor. So I'm going to multiply by that and divide by that as well. So that's this. And then plus, this term already has a 3x plus 1. So we only need the x plus 3 factor here. So we're going to multiply by x plus 3 and x plus 3. In this way, both the terms at the bottom have the same denominator, so they can be compiled together. So this will be 2x and x plus 3, 3x plus 1, and over there you have a times 3x plus 1 plus b times x plus 3 over x plus 3 and 3x plus 1. So now when you have two fractions on both sides of the term, you want to compare them. Okay, since the denominator is the same, you can get them out of the way. If they have to be equal, then their numerators must be equal as well, right? So from this, what we have is 2x must be equals to a times 3x plus 1 plus b times x plus 3. So now, if that is true, how do you even find the values of a and b? So there are clever ways to do that, right? What we're trying to do is, what we tend to do is comparing coefficients. This is the traditional way. Is to compare coefficients, right? And by comparing coefficients, I mean you gotta expand the whole thing up and do all the mumbo jumbo, but we're not gonna do that for now. Just let's stick to the very basic ones and see if we can cleverly come up with something that's gonna help us out. Okay. So we have 2x. In this case, if I pick, I can pick clever values of x. This is gonna be true for any values of x. So if I pick x to be equals to -3 for a second, right? I can plug it in this expression and see I get -6 on this side, and then I'm going to get a times -3 times 3, which is going to give me -9 plus 1, and then b with x as -3 will give you a 0, which means the b factor will go away. So in this case, this equation could be simplified to be -6 equals to a times -8, right? And knowing that from this, you can say a is nothing but 3 over 4. And that's how you solve a. Now to solve for b, we can use the same expression. So I'm gonna lasso that. I'm gonna select this thing. And I copy it over. So now this is the expression. And we know that our a value is nothing but 3 over 4. So that's half of the job done. We still want to solve for the b value. So can I think of a number, a value of x, which will shut off this guy, or which will make this 3x plus 1 equals to 0, right? If I want to shut off that factor, I should pick x equals to -1/3. If I do that, then I'm going to get, on this left side, I'm going to get -2/3, because that will just be that. Then a times 0 plus b times, -1/3 plus 3. So this will make a equals to 0, and then you'll have expressions like this. Let's try to simplify and see what we get. -2/3 on this side, and then -1/3 plus 3 will leave you with 9 and 8. So 8/3 b. Okay, so once we get this, I can kind of like easily resolve this expression by saying that b needs to be equals to -1/4. Okay, so my a is that, and b is that. So knowing this, my decomposed factors, so like 2x, the main thing that we started off with, x plus 3 and 3x plus 1 could be written as a over x plus 3 plus b over 3x plus 1. We told that that's true for what values of a and b? For these values of a and b. So we can plug those in. We can write them as 3/4 and -1/4. And that is the expansion. Okay, once you've expanded it out, taking the integral of this is equivalent to taking the integral of these two separately. Okay, and this integral are easy. I'm not going to do that for this example. We're going to do for the next example. Okay, before we go there, I want to give you a very important thing. Okay, the important rule here to do partial fractions faster. Okay, like how would you even solve this expression if you were to, do it yourself? What you will choose is you'll take the 3/4 outside, and you have 1/x plus 3 dx. So you'll do u substitution here. You'll pick u as x plus 3, then dx equals to du, and you plug it in. You have 3/4 integral of 1/u du, which happens to be 3/4 ln of absolute value of u. When you plug back the u, you get 3/4 ln of x plus 3. Okay, and that's pretty much it. So that's how you solve this. Similar case here. You'll take -1/4, and this expression will just be ln of 3x plus 1 divided by 3. And many of you are wondering, like, how did I just get that 3 at the bottom, right? This is using the chain rule of integration. Okay, some people would have learned it, some people wouldn't have, So I just want to take a second and give you a thought here. So if you're trying to integrate, okay, if you're trying to integrate 1 over something, okay, and that inside part is a linear, okay, if you're trying to do this integral when the inside part is a linear, the expression to that is, the ln of the linear divided by the derivative of the linear. So let's say for the integral 1/3x plus 2. So, because this could be written as a linear plugged in, because 3x plus 2 is a linear, right? And like this, the answer to that will be ln of 3x plus 2, because you're not going to touch the linear. That's the rule. But you got to divide it by the derivative of the linear itself, which happens to be the derivative of 3x plus 2, which is just 3. That's this. What about the integral of, 1 minus x? If you think about it, 1 minus x is also linear. So the integral of 1 over is ln. You got to keep the linear as it is, divided by the derivative of 1 minus x, which happens to be -1. So this would be kind of like helpful in solving, partial fractions quickly. So that's like the first example that we covered. Let's do one more. The second example we're going to cover is, where you have 2x over x squared minus 64. So when you're given this expression, how would you take its integral, right? Now, in this case, again, you see one thing at the bottom which can be factored out, right? X squared minus 64 is something that you can easily factor out using the linear, like the identity formulas, right? This could be written as 2x over x minus 8 and x plus 8, right? Because of, you know, the a squared minus b squared formula. So you can do that. Once you have it in this form, we can write it as, you know, in the partial fraction world. So x minus 8 and x plus 8 could be broken down into two terms because we have two factors, one being x minus 8, the other one being x plus 8, right? And then because the factors itself are linears, the tops have to be constants. Okay, so we got this. Now, when you're saying that this is true, then you have to simplify the expression and solve for a and b. Let's do that. So when you have 2x over x minus 8 and x plus 8, when you cross multiply in this case, you'll have the same x plus 8 here. Basically, we're taking the LCM, right? Divided by. So knowing this, they're the same, you can get rid of them, but you have to compare the numerators as well. So now you have 2x equals to a x plus 8 plus b x minus 8. Knowing this, what you can do is you can, you know, pick a value. So if I choose x to be 8, right, I'm going to get 16 equals to a times 16 plus b times 0. So I've shut off the factor. You know, I've shut off this guy here and got a 0 there. So now I can easily say that my a is just 1 because 16 equals to 16a, and then you can have a equals to 1. Good. Now let's pick another value to shut off a this time. To shut off a, we need to put x equals to minus 8. So minus 8. So you're going to get negative 16 equals to a times 0. And then minus 8 will give you b times minus 16. From this, what you can say is that b is also equals to 1. So once you've solved the a value, solve the b value. Now we can come back to our integral. We know the 2x over could be written as 1, because that's the value of a, plus 1 over, that's just the value, right? So knowing this, you can do that. And taking the integral on the left is just the equivalent of taking the integral of these things separately, right? So when you do that, you know, these are just chain rule of integration because they have linears plugged in inside, you know, the 1 over factor. So we can quickly write this as ln of x minus 8 divided by the derivative of x minus 8. And in this case, that happens to be luckily just 1. And the plus, for that guy, you have ln of x plus 8 divided by the derivative of x plus 8, which is 1, plus c. And that's how you write this answer, right? That's very straightforward. And that was just kind of like an easy peasy cake. But then some of you guys might argue that this question could be solved using u substitution, right? Because what you see here is if you plug in the bottom as u, the top part will become, you know, the 2x is just the derivative of x squared. So that could be solved using u substitution, but that's something that which I will leave you to explore. We're focusing here on method of partial fractions, right? So of course this could be solved by u substitution, and if you were doing this on an exam, you would definitely go with the u substitution world first because that's this easy approach. But here I wanted to highlight the method of partial fractions, and that's how you would do that example. Okay, so let's do one more. Let's go ahead and do an example here where this question is going to be, you know, and then x plus 2. So when you have this kind of scenario, you know, you can write this as, you know, first of all, we got to get rid of the integral sign. We have to write this expression as 6 over x plus 5 could be written as, you know, we got to break it up in two terms because we have two factors. But both of them are linear and they're only repeating once. So no trouble there. And the top has to be constants because both of them are linear factors. Knowing this, you can cross multiply. Now that you're doing this so many times, you kind of know what you got to do is just compare the numerators, right? So the numerators here will be 6 equals to plus b times x plus 5. So now you have a very nice scenario. In this case, you can pick the x value to be, let's say, -2, right? To shut off this first factor, you're going to get 6 because the left side is just going to be 6 no matter whatever you do. 6 times 0 plus, when you plug in -2 into this, you get 3b. So from this, b equals to 2. That's the first thing. Nice. So what if you pick x to b equals to -5 to shut off this factor in this case? So then you're going to have 6 on the left because that's not going to change. Then a times -5 plus 2, which is -3. So your a is going to be equals to -2. Nice. So once we have written it like that, we can plug in them here. The a will become -2. The b will become the 2 here. And integral of this is just equivalent of taking the integral of these individual pieces. So I'm going to lasso that here. So knowing this, in this case, what you can do is you can factor out the -2. And the integral of 1 over x plus 5 by chain rule is ln of x plus 5 divided by the derivative of x plus 5, which is 1. And then over there, you can factor the 2 outside. So integral of 1 over x plus 2 is ln of x plus 2 divided by the integral of, derivative of x plus 2, which is 1 plus c. So that's how you solve this problem again. So far it looks kind of like straightforward now that you've been practicing it for a bit. We are going to look at some twisted examples as well. Some of the twisted examples involve when you have more than one factors coming in, and then, you know, where this just kind of falls apart. So let me try to think of an example that we can, you know, go through here. Let's do this one actually, you know, just like to go over the complicated ones when the method of, you know, shutting off the factors will not work for you. Let's try to see if that one kind of does the job here. So if we were going to have more than 2 factors and something nasty on the top, so we're trying to integrate this guy. We're trying to integrate 3x squared minus 7 over x cubed minus 7x plus 6. So you have a cubic at the bottom and you have a quadratic on the top. And as per the rules, you can still use it because you have, you know, the degrees are going to be changing by 1. The denominator is bigger degree, so we can still use partial fraction only if you can decompose into factors. And if I given that x cubed minus 7x plus 6 could be factored out into x minus 1, x plus 3, and x minus 2. Okay, if we can do that, then our expression could be written as 3x squared minus 7 over x minus 1, x plus 3, x minus 2 equals 2, you know. We got to break them up into 3 separate terms. So x minus 1 here, plus something over x plus 3, plus that over x minus 2. And the tops have to be linears because they're all, you know, constants going to be on top. So knowing that, when you want to cross multiply here, it'll become a little bit complicated, okay? So this a term has x minus 1 already, but it needs the x plus 3 and x minus 2, right? So your expression here will be for the numerators. I'm going to skip the step for the denominator, okay? Minus 7. When you make them into a common thing, so a must have the 2 remaining, so x plus 3 and x minus 2 being multiplied with it. B already has an x plus 3, so it should include the x minus 1 and x minus 2. So x minus 1 and x minus 2. Alright, so keeping that in mind, we can do that. And then the last one will have, it has an x minus 2 already, so it needs an x minus 1 and x plus 3. So see x minus 1 and x plus 3. So we got this expression. Now we got to be very picky, okay? We got to see how we can solve for each one of those values here. So first of all, I'm going to try to shut off this factor. I need to shut off the a factor. If I want to do that, I can either pick x to be minus 3 or x to be 2. I'm going to use the easy one. So if x equals to 2, my expression here in this case will be 3 times 2 squared, which is 12, minus 7. Over there, that will be 0. And this factor also has an x minus 2 there. Do you see that? So the b factor will also be 0. The last one will survive. So c times, 2 minus 1. And, you have 2 plus 3, which is going to be 5. So basically, I have 12 minus 7 is going to give me 5. On the right side, I'm going to have c times 1 times 5, which is 5c. So that tells me the c needs to be 1. Easy. So one of them is solved already. Okay. So we got c equals to 1. Let's do the other. So if we pick, let's try to shut off the b factor now. When you try to shut off the b factor, you pick x equals to the other one. So we're going to pick x equals to 1. When I do that, when we pick x equals to 1, the left side will become 3 minus 7. Now, the a term will survive because it has, so 1 plus 3 and 1 minus 2. That's this. The b factor will go to 0 because that's the point we want to shut it off. And the c term also has an x minus 1, so that will also become 0. So from this, what you get is, on the left side, you're getting a minus 2, right? Not minus 2, my bad, minus 4. Because 3 minus 7 is minus 4. And then from this, when you solve it, you get 4 here. You get minus 1. So basically, you have minus 4a. Which tells you that a needs to be equals to 1. So cool, we solved that. Now let's go to shut off, and solve for b. So we're going to choose x to be minus 3. Because if choosing x to be minus 3, it'll shut off the a term because it has a minus 3. And it'll shut off the c term. So we'll only be left with the b one. Good. Knowing that, you will get 27 minus 7, right? Because 3 times 9 is 27 on the left side here, if you plug it in there. On the right side, the a term will go to 0. The b term will have a minus 3 minus 1, so minus 4. And a minus 3 minus 2, so minus 5. Okay, knowing this, and then the c term will be 0. This tells you it will be 20 equals to 20b. So b needs to be equals to 1 as well. That worked out nicely, surprisingly. Okay, so all of this expansion we can plug in the a, the b, and the c values here. So we can write this as, 1, 1, 1. So that's nice. That was easy. And if you're trying to integrate this expression, it's a piece of cake using the, the chain rule of integration. So the answer for here, I'm going to write it in yellow. Okay. Can I get rid of this things here? I can write the answer to be ln of x minus 1 divided by derivative of x minus 1, which is 1, plus ln of x plus 3 divided by the derivative of x plus 3, which is 1, plus ln of x minus 2 divided by the derivative of x minus 2, which is 1, plus c. So that is the answer. So hopefully, you're getting a hang of it. It'll take some time to practice enough questions to, get used to and get better at it. And that concludes our analysis of this. So I haven't done, any crazy examples in this for partial fractions. As long as you stick to the rules and you know the algebraic manipulations correctly, you should be able to follow along. But if anything doesn't make sense, you can definitely, reach out to me and ask me anytime you want. So that concludes the video on partial fraction expansions. And thanks so much for watching.